Using funding from the Engineering and Physical Sciences Research Council, the University of Bath and Heriot-Watt University have entered a collaboration to develop a new generation of optical fibres for high-power laser delivery. We at the University of Bath develop these fibres, we do some preliminary testing, and then we send them to Heriot-Watt University to be tested for the final application.
Standard fibre uses a solid core. This gives problems due to the optical properties of glass. These problems include spectral transparency, glass absorbs in the infrared, non-linearity and pulse dispersion. These limit the quality of a deliverable pulsed beam. And power delivery. Too much power will simply damage the fibre.
Conventional fibres find applications, particularly in optical telecommunications, but of course in that application it's only necessary to transmit data rather than real useful optical power. Large core fibres are used in industry, for example in laser machining and welding, but the large core which is required to carry the high powers which are needed gives rise to problems in the precision of the delivered beam. It's all very well to use these fibres if you're interested in machining things which are on the millimetre scale. But when you want to machine something really fine, perhaps on the scale of microns, they simply don't work.
And with too much power, the glass melts, giving more absorption and a fuse-like effect as the damage propagates back to the laser source. The novel fibre we have developed is based on hollow core design. This means that the light is guided in air rather than glass, so that the fibre has a much higher power capacity, extended spectral transparency, 100,000 times lower non-linearity and near zero dispersion.
These improved properties enable us to transmit light which would have been previously impossible to deliver through optical fibres, for example in the mid-infrared or with very high optical powers. And that means that we can open up applications which were previously outside of the capabilities of optical fibres. One example of such an application relates to the delivery of laser power at 2.9 microns. This is impossible in conventional silica fibres because silica absorbs 2.9 micron radiation due to the presence of very small amounts of water inside the silica. But the fact that water absorbs light at 2.9 microns also makes that wavelength very valuable for surgery. So we can now deliver both the wavelengths and the optical powers which are required for surgery, and that enables the potential for a new generation of unconstrained surgical instrumentation.
We're only just beginning to discover the full potential of these fibres. They might find application in the transmission of ultra-fast, high-peak power pulses, gas detection, for example methane within infrared.
We're also considering at the moment the possibility of creating a man-portable laser cutting tool, or using a fibre to deliver high-power light to a machine head where it could be used for materials processing. In fact, any application where one needs to deliver laser light over a very broad range of wavelengths with very high precision would benefit from these types of fibres. We've made a lot of progress in this field already, and we're beginning to see the benefits of that. However, we think that there's a long way to go, and we're really just only beginning to find out what might be possible. And we're hoping that we will be able to produce optical fibres which have far lower attenuation than any which have been previously reported. Currently, the most important laser wavelengths are around 1 micron. What's really required is to produce similar kinds of light at very short wavelengths, perhaps into the ultraviolet. That will enable a host of new applications, including, for example, processing of silicon chips in semiconductor fabrication facilities, which would enable us to proceed to a new generation of far cheaper and better computer chips.
EPSRC-sponsored research at Bath and Heriot-Watt continues to advance applications in photonics. For more information on applications in your industrial area for PhD positions, or to see our other research, please get in touch.